Alrighty, let's make sure that's off, and we are good to go. Check the quality. We should be live. I'm not sure how the audio quality is, but by the looks of it, the video seems to be okay. Alright, so welcome to this live stream. Today we are going to be looking at matrix. Oh, my bad. We're going to be looking at matrix properties and what we can use them for and how to set them up given a system of equations. So properties, and let's get straight into it. So let's say we have a system of equations, say 3x plus 4y plus 5z, and 2x plus 3y plus 4z, and x plus 2y plus 3z, and we allow all of them to all equal 0. Well, in this case we can actually write this as what we call a matrix form. We take the coefficients of the x, y, and z, so we get 3 for this one, we get 4 for this one, we get 5 for this one, 2, 3, and 4, 2, 3, 4, and 1, 2, 3. 1, 2, 3. And we put them into this type of table of numbers, what we call a 3 by 3, that was the terrible 3, a 3 by 3 matrix. And by doing that, we can also multiply by our variables. So that will give x, y, and z. And we allow that to be equal to our right-hand side, which is 0, 0, 0. Now we are not going to solve this, but we're just going to try and give a general form for what this would look like if we had arbitrary constants. So we're going to use A1, A2, A3, A4, A5, A6, A7, A8, and A9. Quite a few of the examples you see online will be using A11. What that means is it's the first row of the first column. A12 is the first row, second column. So row by column. And of course we just still have our x, y, z, x, y, z, and our right hand side is just some other set of constants, let's say capital A, capital B, capital C. And this would correspond to the equation a1x plus a2y and a3z is equal to A, and so forward, up to C. And that's the general picture for a 3 by 3 matrix. And now let's go ahead and define a n by n matrix. We're going to use this new terminology, and that is going to be A11, the one I just told you about. So first the row and next the column. Okay, so we have row 1, column 2. Sorry, row 1, column 1, row 1, column 2, up to row 1, column n, and up to row n, column 1, and ANN, and so forward. So we get this, what we call a square matrix. In other words, it's an n by n matrix. And that would correspond for a system of n variables and n equations, but sometimes you can have a system with n variables and m equations. So n is not equal to m. So how would we write this? Well, if we have n variables, that means we would have so basically we would have something like this. We'd have x1 up to xn. So we have n variables that we want to solve for. And in order to solve this properly, we need to have n number of basically results coming out of the equation. So for example, we looked at the 0. We would need n of these. So we would need a column of zeros that have n zeros, if that makes sense. So now, how do we go about solving a n by m matrix? Well, a n by m matrix would have what we call free variables. That's because we don't have enough equations to solve for all the variables, or we have a copy of a equation that is just a constant multiple of another equation. So let's take, for example, 3x plus 4y plus 8z is equal to 0, and 6x plus 8y plus 16z is equal to 0. Well, this is just a constant multiple of 2. So it's got a GCD, sorry, it's not got a GCD of 2, it's actually got a GCD of 3. No, maybe it is 2. Yeah, it is 2. So it's got a GCD of 2, so you can actually factor out that 2. And you see we've got equation 1 and equation 2. As a result, in a matrix, this would turn out to be a row of zeros in a matrix. So let's put that into an example, and that would say we have a random matrix 1, 1, 1, and then now matrix 3, 4, 8, and 6, 8, 16. And we will come back to this when we introduce you guys to elementary row operations, which we actually might start on doing in a minute, but hopefully that all makes sense. So, for example, take a row operation, we just can do a few things. We can multiply by a constant apart from 0, we can subtract rows, and we can add rows. So in this case we would want to have row 3 go to row 3, subtracting 2 lots of row 1. Sorry, not of row 1, of row 2. And that would give us 1, 1, 1, 3, 4, 8, and 0, 0, 0. Notice that the first row and the second row are unaffected.